Hi everybody, welcome to another video in Statistics, Chapter 8, Sampling Distribution. On the previous chapter we learned about normal distribution of a single random variable. But this time we focus on the statistic of a sample, and that statistic itself will have a will have a distribution as well. So we say X bar or some similar statistic are random variables because the values vary from sample to sample. The sampling distribution of statistic is the probability distribution for all possible values of statistic computed from a sample of size n. For example, if we talk about let's say everybody in the college, and we pick a sample of 30, and we say what is the average age of those 30 students, for example. In that case, the distribution of that would be comparing to every possible sample of 30, so that would be a lot. So pick 30 people, 30 students, get a mean, for example, and then we pick another 30 students, get another mean. So the distribution of that simple mean will compare to the rest of the sample of size 30, so that would be a lot. So the sampling distribution of a statistic is probability distribution for all possible values of statistic computed from sample size n. The sampling distribution of samples mean X bar is the probability distribution for all possible values of the random variable X bar computed from the sample of size n. So pretty much, as we said, for example, we find the mean and we compare that to every possible mean of the same size samples. So all the samples of the same size, we compare that with the one we have. Right. So the nice thing about this is also the calculation will be very similar to what we have in chapter 7. Right. And look at some examples. The ways of pennies minute after 1982 are approximately normally distributed. So we have normally distributed population, and we have the mean, and we have standard deviation. Approximate the sampling distribution of the sample mean obtained from 200 random samples of sample size n. Alright, now of course we have millions and millions of, in this case, what is that? Pennies minute after 1982, so there are a bunch of them. Now what we do is we're going to collect 200 samples, and this sample have 5 of them, have 5 cones, and we find the mean of those 5 cones. So we collect 200 samples of size 5, and for those each sample of size 5 we find the mean, and this is what we have on those table, on those data. And if we plot that in the histogram, this looks like a bell curve. So because originally the population is normally distributed, the sample mean will follow the same. Now if we increase the size from 5 to 20, we do the same thing, collect 200 samples, and this sample has 20, and we find the mean of those 20 in each sample, and a histogram like that. Of course the sample size here 20 is even more like a bell shape. Right, here the math. I suppose that a random sample of size n is drawn from a large population with the mean and standard deviation. The sampling distribution x have the mean mu of x and standard deviation of sigma of x given by this. Right. So suppose a simple random of size n is drawn from a large population with mean and standard deviation. So this comes from the population, and the mean of the mean, we said the mean of x bar is the same as the population, and the standard deviation, in this case we call the standard error of the mean, is sigma divided by square root of n. So now we have mu is the population mean, and sigma population standard deviation. In this case, both of those come from a population that is normally distributed, and n will be the sample size. It says that if the random variable x is normally distributed, the sampling distribution of the sample mean x bar is also normally distributed. So this comes from a population that is normally distributed. So in that case, the mean is also normally distributed. Right. So here's a picture. In this example, we have every pennies after 1982. The weights are normally distributed. So each one of them, if we talk about the weight of individual one, will be normally distributed. Now, what we're not interested in is no longer one individual. Now we're interested in the mean of a sample. Let's say the sample could be the size of 20, the size of 5. So when we have the sample, each sample we find the mean of that sample, and the mean of that sample will be normally distributed as well if it draws from the normally distributed population. Right. But the math, the mean of the sample mean is the same as the mean of the population, and the standard error of the mean is standard deviation divided by square root of n, where n is the sample size. Right, so the math is straightforward. Let mu be 38, sigma 24, n is equal to 16. What is the mean of the mean? Well, that is the same as the mean of the population, which is 38. Next, standard error of the mean will be equal to sigma divided by square root of n. Sigma is 24, square root of n is 4. So 24 divided by 4 is 6. Right, straightforward, right? So the mean of the sample means is equal to the mean of the population, and the standard deviation of the sample mean is equal to standard deviation of population divided by square root of n. Right, so that's what we have. So the calculation is very simple. The mean of all the sample mean is the same as the population, and the standard error of the sample mean is standard deviation of the population divided by square root of n. So we have 10 divided by square root of 25. Square of 25 is 5, 10 divided by 5 is 2. Yeah, so it's very straightforward calculation. And later on we'll see that when we have the mean and standard deviation, we can find the distribution. Or if we know the distribution, we can find the values x or z. Alright, now our rainbow of size n is to be drawn from the population of the mean 600 and 200. What sample size would be necessary in order to ensure that the standard error of 25? Right, so we have the mean of that. Right, I think this problem is a typo. The 200 here is sigma. What sample size n, what sample would be necessary in order to ensure the standard error of 25? So standard error of the sample mean is equal to standard deviation divided by square root of n. So put all the number we know, standard error to be 25, standard deviation 200, and the sample size we don't know, because that's what we asked to find, the size of the sample. Right, so what I do is cross multiplying here. 25 square root of n equal to 200. We can divide by 25 on both sides. So we have square root of n equal to 8, and then we square both sides. N equal to 8 squared is 64. Right. So 200 divided by 25, and then we square 64. Right. Right. So we can calculate the mean of the sample mean and the standard error of the sample mean. With that, we can calculate the distribution of the values. We'll see. Right. The weight of the pennies minute after 1982 are approximately normal distributed with the mean and standard deviation. What is the probability that a simple random of size of 10 pennies? So we know that's going to be n equal to 10. What is we obtain the mean at least 2.465. Right, now we have the mean of the population and the standard deviation of the population is that. What is the probability that in the sample random? Right, so first we need to find the mean, which is the mean of the sample mean will be the same as of the population, which is 2.46. And the standard error of the sample mean is equal to sigma standard deviation, which is that divided by square root of n. N is 10. Sample size 10. Right, so we have 0.02 divided by square root of 10. We have that 0.0063. Alright, just going to keep that number. Now, what we have is find that the sample mean will be at least 2.465. So first we plot the mean. We draw the normal curve. The mean is 2.46, and we want at least 2.465, meaning greater than or equal to. So it would be very easily to find the area. It's going to be normal CDF. So in this case, we find from that value to a very big number, so we can use that. Right, so second distribution, normal CDF. The left bound is 2.465, and the upper is very big number. The mean is 2.46, standard deviation 0.0063. Of course, we can get the more accurate number, but that will be enough. So when we do that, we have 0.214. So that means 21.4%. So the question is, what is the probability? And the probability is 0.214. Right? So simple. We have the normal curve, and we just find the sample, the mean of the sample means and the standard error of the sample mean. And after that, we find the error using normal CDF easily. Right, next. The body temperature of adults are normally distributed with the mean of 98.6 and standard deviation of 0.6. If 25 adults are randomly selected, find the probability that the mean of temperature is less than 99. So once again, we're going to select a sample mean of 25, and we see how is that distributed, how the distribution of that sample mean. Right, so first we have to find the mean of the sample mean, which is the same as the mean of the population, 98.6 degree Fahrenheit. Now standard error of the sample mean is standard deviation divided by square root of n. This time n is equal to 25. So standard deviation is 0.6 divided by square root of 25. Square root of 25 is 5. 0.6 divided by 5 is 0.12. So we have the mean and the standard deviation. So it's ready to go. Right? So 0.6 divided by square root of 25. 0.12. Right, that's good enough. Next, the question is find the probability that the mean is less than 99 degrees. So we draw the normal curve. The mean is 98.6. And we want it less than 99. So 99 of course is bigger than 98.6. So it will be in that side. And as for the probability, so we will find the area. The area will be normal CDF. We go from a very small number. Very small number. Because this is 98.6, so we have to choose a few more nines. Go to 99. Yeah, so on the left. And then the mean is 98.6. The standard deviation is 0.12. Yeah, so we just like that. Distribution CDF negative upper 99 mean 98.6 and the standard deviation 0.12. And we have 0.99957. Right. So the mean of 25 adults, if we want the mean temperature is 99 degree Fahrenheit or less, it will be 99.96% of it. Now if we use StatCrunch, right, so once again we have to calculate the mean and standard deviation. After that we just go to statistic calculators and go for normal. Right, so this is the mean we know is 98.6 and the standard deviation or the standard error we have 0.12, and then we want it less than 99 and we compute. So that's what we have, more exact answer. So once again what we need is the mean, in this case the mean of the sample means and the standard deviation, in this case the standard error of the sample mean. And after that we just find the values, the area easily. The furnace repair bills are normally distributed with the mean of $267 and the standard deviation of $25. If 100 of these repair bills are randomly selected, find the probability that they have a mean cost between $266 and $270. Sorry, I read the problem, but I forgot to change to the note. Right. Once again, in this problem, we have the mean. This is the population is normally distributed. The mean is this, and the standard deviation is that. If 100 of this repair bill, so 100, so that will be n is 100. Find the probability that they have the mean between 266 and 270. So first, the mean of the sample mean. is the same as the mean of the population, which is 267. Next, the standard error. Of sample mean. Right. So, standard error of the sample mean is equal to standard deviation divided by square root of n. Standard deviation in this case is $25 and square root of 100, which is 10. 25 by 10 is 2.5. So we have the mean and standard deviation. The rest is just a calculation. So we know the mean in the middle is 267. And then we want find the probability that the cost between 266 and 270. 266 is on this side and 270 is on this side. And we want to find the area or the probability. Right, so it's normal CDF from here to there, and the mean and standard deviation. So straightforward, right? Normal CDF of 266 to 270, and the mean is 267. Standard deviation or the standard error of sample mean is 2.5. Right, so that's what we have. Second distribution, normal CDF. Alright, so we go from 266 to 270, and the mean of the population is 267, and standard deviation 2.5. So that's what we have. So it's about 54%. Right. So whether we find between two values on the left or on the right, it is the same. We just need to determine the sample mean and the standard error of the sample mean. So pretty much the mean and standard deviation. Right. So what we have earlier is that the population has to be normally distributed for it to work. But here we have an example here that the first part is we have non-normal population. So, for example, if we talk about a fair dice, this is uniform distribution. All of them have the same values, and we find the mean and standard deviation from that. Now we estimate the sampling distribution of x by obtaining 200 sample of size n equal to 4, n equal to 10, and n equal to 30. So that's a lot. As you see, the bigger the number, the more likely that the shape will follow the normal distribution, so it has the bell curve. So here we have the central limit theorem. Regardless of the shape of the underlying population, so it doesn't matter what the population go by the certain distribution, we don't care about that. It's like the sampling distribution of x bar become approximately normal when the sample size increase. And said how big is sufficient, and the answer with that is 30. So if n is equal to 30, then we don't need to do sampling distribution for the population. Right, let's look at the example. The owner of the computer repair shop have determined that the daily revenue has 7,200 and standard deviation of that. So we know from the population the mean of the sample mean is 7,200, and the standard deviation or the standard error of the sample mean is 1,200. The daily revenue for the total next will be 30 days. Right. question is, what is the probability that the mean daily revenue for the next 30 days will exceed 7,500? So once again, we're not talking about a single individual. We talk about a sample of size 30 in this case. So I will draw the normal curve. And we know the mean in the middle will be 7,200. And standard deviation of 1,200. The daily revenue total for the next 30 days will be monitored. And what is the probability that the mean of daily revenue for the next 30 days will exceed 7,500? So now we have the sample of 30, and we find what is the probability of getting that particular characteristic of more than 7,500. So at 7,500, we calculate this, and it will be normal CDF. The mean 7,200, and that I forgot. The formula was sigma by square root of n. So sigma 1200 divided by square root of n, square of 100, which is 10. So that is 120. I don't know why I need a calculator for that. Right, so the mean of the population mean, the mean of the sample mean is that, and the standard deviation of the sample mean is that. And sorry, I've got the wrong syntax. The normal CDF will go from 7,500 to infinity, so very big number. And the mean is 7,200, and standard deviation of 120. I just put that in the calculator. Second variable, normal CDF, and we have from 7,500 to infinity. The mean 7,200, and the sample size 30. But we know the mean is standard deviation 120. So that area is equal to 0.0062. Right. So just like the last problem, if we know the mean and the standard deviation, we can find the distribution of that variable with some characteristic. This one we said exceeds 7,500. Right. Next, John has 6 bills. We won't be able to do this yet. John has 6 bills of paper money with the following 1, 5, 10, 20, 50, and $100. If we select 3 bills at random, find the probability of selecting a group that average at least 26. So the problem here is this is not normally distributed. So in that case, we have to do that differently. The way differently here is we just have to list. We have select 3 bills at a time. So that would be a 1, a 5, and a 10, of 1, a 5, and a 20, a 1, the 5, and the 50, the 1, the 5, and the 100. So we're going to list all the possible sample of sine 3, and we'll find the mean of that. And after that, we find the distribution. Right? So might not finish the whole problem, but this is the idea. For 3 of them, the mean of this will be 16 divided by 3, 5.3 something. This is 26. This is close to 9. I'm sorry, that was 29, right? Divide by 3. So 9.67. Not 29. 26. So this mean is 8.67. the mean of this 56 divided by 3. So it's 18.67, and 106 divided by 3. 35.33. Right. So we list, and of course we're going to list more of that, and we just count how many we have with the average at least meaning 26 or higher, like a sample here, and we just list all the possible sample. Right. So as you see, if the problem is not the normal distribution, then that will be a problem. So if the population is normal distribution, then the mean of the sample mean, let me put that again. So if the population is normally distributed, then the mean of the sample is also normally distributed. Now, if the population is not normally distributed, we still be able to do it, but we have to select the sample size very big, and big is meaning more than 30. This one we don't know. This one, it is not normally distributed, and the sample is size 3, so we won't be able to use that theorem. And with that, we stop chapter 8, the first part of chapter 8 here. Once again, we need two possibilities. Number one, the population is normally distributed. In that case, we find the mean and standard deviation. If it is not normally distributed, we want the population to, we want the sample with the big size, the big meaning 30 or more. So with that, I finish this section, and we'll pick it up in another video in statistics. Thank you for watching.